Hey guys, so in this video I'm going to introduce integration and arc length, and then also I'm going to explain how the formula for arc length is derived. And I apologize in advance if I sound a little stuffy. I am. I'm just getting over, or I have a cold, so, but the show must go on. Okay, so let's talk about this. So let's say that we want to find the length of the curve y equals square root of x minus 2 from x equals 2 to 6. Okay, so first of all, just what are we talking about? So we're talking about a curve that looks like this. And so arc length, so curves and arcs, it's the same thing. So I want to find the length of the curve or the length of the arc. Okay, and maybe just to like motivate this, I want to think about how does calculus fit into this argument. And honestly, I think this is a really great question to ponder of like, where do you think this video is going? So if I were you, I would write down a guess of maybe how this is going to work. Just write it on the side of the paper, pause the video, and then hit play just to see if you're right. It's like cool to see how your intuition kind of plays into this. Okay, so before I can get into arc length and the formula for this, I want to go back to algebra for a moment because we're going to use some ideas from algebra to help us. So my question is, what is the length of a line segment from x1, y1 to x2, y2? Okay, so in this case, this is actually an algebra question, so if you're a calculus student, I think this would be great to just see if you remember this formula. You can draw a line segment. It's a straight line segment, and then just write out the formula. Hit play when you're ready. Okay, so here's my x1, y1, and my x2, y2. So if I want to figure out what is the length of this line segment, it's just a general line segment. So we actually kind of rely on the fact that like there's kind of this assumed invisible right triangle here formed by these lines. And I can find the lengths of these sides. So the length of the green side is just x2 minus x1. So write the larger number minus the smaller number. Same thing for this length. So this is y2 minus y1, and then this length here is d. And this will be the distance from this point to this point. Okay, so if I'm thinking back to my right triangle Pythagorean theorem properties, I can totally just use this property, right? D squared equals just a squared plus b squared, but instead of having a squared and b squared, right, I have this length of this side squared plus this length of this side squared. But it's still really just the Pythagorean theorem, right? And then if I wanted to know, so what is the actual just length of d, so then all I'd have to do is find the square root. Okay, so this formula is actually going to help us determine the length of our line segment. So what I want to ask is like, how can we apply the idea of a line segment, just in general, to this curve? And maybe you already kind of had an idea about this. So the idea would be that we'd probably want to separate this curve into smaller line segments like you see here. And then we'd want to connect those line segments. So there's now all these tiny lines. And then we could just find the length of each one of these tiny line segments. And of course we know that like this many line segments maybe won't be the greatest estimate for the curve, right? Because this thing is curved and these lines are straight. So to get a better estimate, of course, we would want to just continue to chop this line up to all these tiny little line segments, and so better estimates will have more segments. And so then the best estimate would have how many line segments? It would have an infinite amount of line segments. And so once we kind of get to the idea of like, oh, I want to chop this up to an infinite amount of pieces, well, that's like a Riemann sum in disguise, right? So let's talk about like the idea behind this Riemann sum. Because once you have a Riemann sum, then somewhere around the corner you have integration. So the idea behind the Riemann sum is, so this limit is talking about getting an infinite number of line segments. So what I would want to do is I'd want to have my line segments. I have n of them, but n is going to infinity. So I have all these line segments. And all I would have to do then to find the length of my curve is to sum up the length of each line segment. So I find the length of each line segment, I add them all up, I get the length of the curve. Okay, so another way to write this idea, we're going to write it like this, where this L sub k now represents, so this sub k language represents the idea that we're summing up all of these different line segments. Okay, so now we're talking about line segments here. So I'm probably going to go back to this idea, right, that we were just talking about. And we just need to modify now this formula for our needs. So this is going to come, this is going to come full circle. So for now, I just want to change the way that we're thinking about this a little bit. A lot of times, you know, we have a lot of the same formulas and then we'll modify them and change the way that we think about them just for the application. So in this case, instead of calling this x2 minus x1, I want to call this delta x. And what that means is the change in x, so the change from here to here. And then we've got the y's, y2 minus y1, that'll be delta y. Okay, so keep that in mind. So this formula now I can rewrite as the square root of delta x squared plus delta y squared. Okay, so to show how else we want to modify this formula, there's one other thing that we need to do. So we're not done modifying that formula. That's only the first step. So what we're going to do is we need to take a moment to review the mean value theorem, which is something you learned back when you learned derivatives. But there's something in the mean value theorem that we're going to apply into this formula. So trust me, this is going somewhere. Okay, so just to remind you what the mean value theorem is. So we have this function f of x, it's continuous on a closed interval and it's differentiable on the interior. The real important thing that we need to remember about the mean value theorem is that it says this: there is at least one point C in that interval where f prime of C equals f of b minus f of a over b minus a. So whether you remember this super well or not, doesn't matter. And I'll just remind you, like, what does this actually mean? So the idea behind the mean value theorem is that if I have these two random points A and B, there will be some point C in this interval from A to B where this happens. So where there's a point on the curve that has the same slope as the line that connects these 2 points. So that's what the mean value theorem is really getting at. Okay, so I need to take this formula, and this is all going somewhere. So what I want to do is I just want to modify it once again. So this top part, this is still just talking about a change in y values. So f of b minus f of a is talking about change in y. The bottom part's still talking about changes in x's. So I actually want to rewrite the mean value theorem then as f prime of c of delta y over delta x. And I'm going to go one step farther with this. So I'm going to multiply both sides by delta x so that I can rewrite this as delta y equals delta x times f prime of c. Okay, so this is going to come back in a second. The other thing that I want to remind you of is that our c, this c, sits somewhere between a and b, so somewhere in this interval. This is all going to come full circle, so I'm just kind of throwing this stuff out there. You just kind of keep it in the back of your mind. Okay, so now we can go back to the Riemann sum. So, I just talked about this. The lengths of these line segments we've represented with this formula, right? This is the distance formula with the delta x sub k and the delta y sub k. Now, the thing is that usually with a Riemann sum, we would prefer to have everything in terms of x. So I would like to rewrite this y sub k. And so I can do that, right, by using this thing right here, right? This is what we need. So this is why we talked about the mean value theorem, because it's going to allow me to switch out my delta y in terms of x. Now, the other thing I want to point out here is I want to talk a little bit about this C being between A and B, because I'm going to do something in a second that could blow your mind. So I want to kind of prepare you for it. Okay, so I'm going to use this fact. But I also want to just talk about what happens with C when it's wedged between A and B. So our goal in this line segment stuff, we want to have this infinite amount of line segments. So what will the length of each line segment be? The length of each line segment will be as close to 0 as possible. We'll just call it 0. Okay, so what does that mean then for this? If this C is wedged between a line segment of length 0, then what is the actual line segment? It's not going to be B anymore. It's not going to be wedged between A and B. It's kind of wedged between the same values. So more importantly, the thing I want to point out here is, so if C were wedged between two x's, then what does that mean about C? That means that C just equals x. So again, just kind of hold this in the back of your mind. And you'll see where this is all going in a second, so just remember this. Okay, so now I can keep going back to my Riemann sum, and I can replace this right here with our mean value theorem. So I've got f prime c times delta x sub k. We know where that comes from. Okay, so I need a little more space. And the next thing that I want to do here is now I just want to do a little algebra. So now I'm not really doing anything except algebra. So this squared exponent, I just want to apply it to each part of this product. So I can rewrite this inside now as delta x squared, f prime c squared, and delta x sub k squared. Okay, and now that I've taken the time to distribute that exponent as I did, I actually noticed that I've got these two x sub k's. So I've got an x sub k here and an x sub k here, which means that I can factor them out. And so if I factor out the x sub k, so what is that going to leave me with? 1 plus f prime c of 2. Or f prime c squared. Sorry, I told you I've got a cold, so my brain's a little weird. Okay, so cool. Well, now that I've done this, I can just use a property of working with square roots, and I can actually just break this up into two separate square roots. And the cool thing about that is then that this square root will cancel out this squared term. So now here's what I'm left with. I have made that one substitution from the mean value theorem, and I've rewritten my theorem, my sum like so. And so now this is actually a Riemann sum, and this can be rewritten as an integral. So I've talked about a few other Riemann sums throughout this chapter. So hopefully you've started to notice, so whenever you have this delta x sub k, that is always going to stand for your dx. And in this case, what does the delta x sub k stand for? So it stands for the length of your line segment, which we're trying to get as close to 0 as possible. And then remember, if I actually achieve my goal then of getting all these line segments to be as close to 0 as possible, what does that mean? That means that my c is no longer a c, it's just going to every single x value in each interval. So what that allows me to do then is that allows me to rewrite this as what you see here. And this, my friends, is the formula for arc length. So, arc length. If f prime is continuous on a closed interval, then the length of f of x from x equals a to x equals b can be found by the square root of 1 plus f prime of x squared. So it's actually like a pretty nice, easy little package of a formula. And another way that we could write this is instead of writing f prime of x, we could also substitute that as dy over dx squared, tomato, tomato, doesn't matter which way you want to think of it. Okay, so now that we've gone through that, let's just talk about an example real quick. So let's say I want to find the length of the curve y equals 4x to the 3 halves from x equals 0 to x equals 1. Well, the first thing that I need to know is what is the derivative. So I can go ahead and find my dy dx just by using my standard derivative formulas. So this is going to work out to be 6x to the 1 half. And then I know that I need to square that ultimately, so I'll just go ahead and square that right now. Now x to the 1 half can be rewritten as the square root of x, so I can just rewrite as you see here. So this whole thing simplifies then to just 36x. Okay, and so now that I know that this derivative squared is 36x, so now I can go ahead and bust out my formula, right? And I can just replace my dy dx squared with my 36x. And I know I'm going from 0 to 1. So here's what I need to integrate now. So this is all we have to focus on. So I'm going to focus on this square root of 1 plus 36x. Now the only way that I can integrate this is by using substitution. So in this case, I'm going to set my u equal to 36x plus 1, or 1 plus 36x. I just wrote it in the wrong order because I have cold brain right now. And then I can take the derivative. Now there's no 36 on the outside here, so I've just got to rewrite this as 1 over 36 du equals dx. Okay, and so then next, so if x equals 1, then u is going to equal 37, and if x equals 0, u equals 1. I like to change my limits of integration. So I can plug in everything here and integrate what you see. And so if I integrate, so here's what I'll get, and then here's everything after I plug it in. This is not a beautiful number, so I just left this as 37 3 halves minus 1 over 54. Okay, so that's kind of your intro to arc length. In another video, I'll talk about a little bit more with this, but I think I'll leave that here. I will catch you guys in the next video.